Welcome to another video on the continuation of projectiles. So if you've watched the initial video, we basically dealt with trying to understand what a projectile is and trying to make use of the formulas that we have, trying to solve what a projectile is. So in this video, I want us to have a more intuitive understanding of what a projectile is. So what is a projectile? What a projectile is, and how we got to arrive at those formulas first. So before this video, I hope you understand the following concept that I will write down now. So the concept of what the uniform velocity motion is. So what a uniform velocity motion is: a uniformly accelerated motion. Uniformly accelerated motion, and what the equations of motions are. So the equations of motions are. So we are going to be relying on these concepts throughout this video. But one thing I want us to do so far, first of all, is to try to recap what a projectile is. So a projectile is an object that is launched into the air and allowed to move under the influence of gravity. So whenever you launch an object into the air and it moves under the influence of gravity alone, we have a projectile. So you could either throw it at an angle to the horizontal at a certain angle theta, or you can draw it vertically upward, in which case it will be angle 90 to the horizontal, or you could actually just fling it around too, in which case this will be at angle 0 degrees to the ground. So in the case of where you throw it vertically upward, we can summarize and say it is a vertical projection. So that's the scenario A. And in the case you just fling it like a frisbee, like a flat surface, and throw it around, we say that is a horizontal projection. And every other way, we don't even call it with a name, but it has an angle theta that is not 90 degree or 0 degree. So in 0 degree, it is parallel to the ground. So we don't have those two situations here. We have another angle, which is what? Theta. And then one other thing is that we told you that we have three quantities. We have the time of flight. So we have the time of flight, the horizontal range, and the maximum height. So we have these three things to note about projectiles. Let's discuss what these three things are again. So the first one is time of flight. So what is time of flight? So basically, your time of flight is the total time it takes for your projectile to get launched into the air and return to the same horizontal level that it was initially projected from. So the same horizontal level. If you throw it on top of a high building, your time of flight will be the total time it took it to go up and back to the same top of the level of the high building you were on. The time of flight does not include the time it took to fall to the ground in case it missed the top of the building, right? So that's what your time of flight is all about. The time it takes for the projectile to go all the way up and return to the same horizontal level from which it was projected. If this happens to be on top of a building and then when on its way back it misses the building to fall all the way down, so that time it is falling all the way down is not part of the calculation of time of flight. So the second thing is horizontal range. Horizontal range is the difference between the initial level where it was projected and where it finally landed to on that same horizontal ground. So that place, the distance between the initial point of projection and where it landed to, is the horizontal range. So it is a horizontal thing. That's why we say horizontal range. And the third thing we have is the maximum height. So that's the difference in height between where you initially threw it and the highest point it reached. So that's the maximum height. So we have these three things that we've hopefully understood from the first part of the topic. Your time of flight, which the symbol is capital T, your horizontal range, your R, and your maximum height, which is H. So those are the three things. So now let's also look here. Now I told you that three things are important for you to catch up with this video. And the first thing is your uniform velocity motion, your uniformly accelerated motion, and the third thing is the equations of motion. So why is this important? Now let us imagine a projectile motion. For the first case now, let us imagine we have a projectile motion. A projectile motion could be a goalkeeper kicking the ball into the field, or someone who wants to play a free kick. So now the motion goes on like this. It is at an angle theta to the surface of the ground. Now that velocity, we could take it that is going to kick it with a certain velocity u. Let's signify that with a u. Yeah, now that's the initial velocity. So that motion, I hope you can agree with me that it is split into two ways. It is both going up in the field and it's also going across the field as well. So we're using the example of the free kick, for example. Hopefully you don't want to shoot your football at a vertical up direction, or you don't want to, it's not really, and you don't want to just pass it horizontally across the field. You want to give it a little bit of a vertical motion up and an across motion through the field, hopefully towards your goal post, right? So that is what the two things that are going on here. We have two kinds of motion going on in our projectile. We have the horizontal motion and the vertical motion. The vertical motion going up, and then your horizontal motion going across. Those are the two type of motion that is going on here. So let us indicate it now. So we have two kinds of motion now. The first one is your vertical motion. So the vertical motion, and the next one is your horizontal motion. So your horizontal motion, so for any projectile that is that is at an angle to the horizontal, at an angle theta. So we have both the vertical motion and the horizontal motion. So we can see that there's an angle theta that the distance. If it is a vertically upward motion, there is no horizontal side to it. If I throw an object up and return, like if I throw an object up and then this thing, there is no horizontal motion at all. But if I fling an object across, there is no vertical motion across, so at all in that sense either. So the sense I'm actually talking about is when is not when we have an angle 90 throwing up or an angle 0 throwing across. It is when we have any other angle in between that. So this your angle theta is not 90 and is not 0. So those are the two things that you need to actually pay attention to. So we have the vertical motion and the horizontal motion, like I said. So what is special about splitting it like this? The reality is that our eyes, we know that mathematically that these two things have to be occurring at the same time, but our eyes and our brain have merged them into two, that we see it as going around, like it's going up and then coming down, moving vertically and horizontally at the same time. But in terms of the mathematics, we actually can't do them together, right? The vertical motion has a particular condition to it, and the horizontal motion has its own condition to it as well, and they are really not the same conditions, and that's what this video is really trying to bring about. So the first one we need to understand is let's talk about the vertical motion. The vertical motion. So if we return to the definition of what a projectile is, I said a projectile is an object that is launched into the air and allowed to move under the influence of gravity. So your vertical motion is always affected by gravity. It is always affected by gravity. So your vertical motion is the one that is always affected by gravity. And since gravity always gives a uniform acceleration or deceleration to an object, your vertical motion is your uniformly accelerated motion. It has a uniform acceleration. That means the velocity will change by the same amount in the same time interval. So that is what your vertical motion is. Your vertical motion is a uniformly accelerated motion. So that's what your vertical motion is. And on the other hand, we have the horizontal motion. Now this your horizontal motion now, there is no effect of gravity there, because your gravity only acts upwards and downwards. There is no effect of gravity there, and there is no friction or force. I mean, there is a friction in the air, but it's totally very negligible. Yeah, and we don't call it friction, we call it viscosity. But in this case, we assume it is totally negligible. So if there's no friction, there's no anything, there's no any other force coming here, it looks like we could have our uniform velocity motion, our uniform motion, in which the object keeps going with the same speed throughout our motion, the uniform velocity motion. So that is it now. So uniform velocity motion, you are taking the same speed throughout your motion. Throughout the entire motion is your uniform, your horizontal distance. So when we split our motion into two, we have the vertical motion, which is a uniformly accelerated motion, and our horizontal motion, which is a uniform velocity motion. So that is the two cases that are going on in our projectile at the same time every time. And then by the time we are done with the entire derivation and explanation, you will see that the mathematics basically checks out. But we just needed to see what this is all about. And as a summary, the third thing I asked us to learn, the equations of motion. What are the equations of motion? One more time. So the equations of motion, your equations of motion, we have three of them. The first one is your v equals to u plus at. The second one is v squared equals to u squared plus 2as, and the third one is s is equals to ut plus half at squared. So those are the three equations of motion, and the condition to using these three is that your acceleration is uniform. It has to be a uniformly accelerated motion. So acceleration is uniform. So in order to use these three, it has to be a uniformly accelerated motion. And then if you are having a uniform velocity motion, so we should recall that in a uniform velocity motion, if you have a uniform velocity motion, your acceleration is 0. Think of it well. Why is acceleration equal to 0? I mean, if your velocity is not changing, as it is in the case of a uniform velocity motion, your acceleration is 0 because there is no change at all. Acceleration is a change in velocity. So since there is no change in velocity, acceleration is 0. And if you substitute your acceleration in 0, your equation 1, 2, 3 reduced to 1 is v is equals to u. Your I says your v squared equals to u squared, and your I says your s is equals to ut, which is the only one that is actually useful. So that's the case of having your distance is equals to speed times time. That is the summary to the third one, because s is distance, u is initial velocity, which is also the same as your final velocity here, and then we have time. So I hope this initial first section I've kind of like introduced what the vertical and the initial I said vertical and horizontal motion of a projectile is all about. So we'll take a little bit of break here. In the next section, we'll talk about how all of this applies to the actual mathematics of the time of flight, the horizontal range, and the maximum height. Alright, so let's get back into this video on projectiles as we're explaining. So the first thing is that we understand that your projectiles is split into two different motions occurring at the same time, the vertical motion and the horizontal motion, right? So that's what we have for the projectile motions. So one thing you should do note is that we have your what's it called, your vertical motion is a uniformly accelerated motion, while your horizontal motion is a uniform velocity motion. So before we actually get into the mathematics and deriving equations and all of that, we should look into your vectors. So anytime we have a vector, we can actually split it into components. right? If you think of your initial velocity now, think of this your u. It is a vector component. I mean, velocities are vectors anyway, so, and it is inclined as theta to the horizontal. So that means you can split it into the horizontal component and the vertical component, and that's the idea we are going to take now. Since we actually do need the vertical and horizontal motion anyway, we're going to take the velocities as both in their what's it called, your horizontal components and your vertical components, and that's what we do right now. All right, so let us assume that the initial velocity of the distance, that we have the following quantities around it. So we have your ux, right, and your uy. And what are they now? So you have your initial velocity and your angle theta, the angle of projection of your projectile. So your u is the initial velocity. If you are splitting it into the components, remember that your u is the initial, the horizontal component of initial velocity. We should put that down there. And then we have this to be the vertical component of initial velocity, like that. So we have that. So remember, we have something like this going on there. We have this representing your u, and then we want to have the component here, and then this. So this makes an angle 90. We have our ux and our uy, and they are all at an angle theta. So to summarize the brief story, by applying your SOHCAHTOA, you get your ux is equals to u cos theta, and your uy is equals to u sine theta. So let's work with this now. So this is what our splitting of a thing just gave us. Your ux is u cos theta, and your uy is u sine theta. So we have these two things there now. So the next thing for you to do is for you to consider the motion as it is now. So we have your vertical motion and your horizontal motion, and I feel we should start with the vertical motion because that's more interesting. That's your uniformly accelerated motion. So let's get with it now. So your what's it called? So let's deal with the vertical motion now. The vertical motion. So initially now, for the vertical motion, we are not going to deal with your ux, right? Because your ux is the horizontal component. So we don't want to work with the horizontal component. We want to work with the vertical component because that's the one that actually goes up, not the one that goes across. So is that part of the actual u that was provided that goes up? Is that section of it that goes up? So your uy is now what? Your u sine theta. And since something is going up, your acceleration is going to be minus g. So now we have these two things working out for us. So the next thing for us to try to find out is to use the equations of motions which we have. And let's try with the first one. The first one says that the equation 1 tells us that your v is equals to u plus at from our equations of motion. If we now put it into this domain of your vertical motion now, we are going to have your v now is going to be a vy, your vy, and then is now going to be what? U sine theta, because that's your ux. Okay, let me not put any formula there now first of all. So we're going to have your vy is equals to your uy, then we have it to be minus gt, right? Your gt, that's your that there. But then one thing we know is that because this is saying your vertical component of the final velocity is equals to the vertical component of the initial velocity minus the acceleration due to gravity multiplied by the time at any point, right? So that is a standard equation. Let's call it equation 1. The advantage of this formula is that you can use it to get the vertical component of the velocity, the final, at any time of your projectile motion. And I don't think that's a convenience that your initial formulas that we had your h, your t, and your r they gave. You couldn't have done that without having to understand this simple thing. So in any case, this could be it could be an interesting problem, that it could be something that is necessary, and we've seen how we just got it. That so your Vy is the vertical component of the final velocity there. So one thing about it is that, you know, your projectile is still going up, it's still moving up, and at some certain points it's going to reach the maximum height, and at that maximum height your Vy is going to be a 0. Why is it 0? Because all of the velocity, everything that's supposed to take it even more to the way up, is now finally what? 0, because it doesn't go any higher than that. So that's what we are going to have that to be a 0. So we know that at maximum height, your Vy must be equal to a 0. So if we substitute that there, we have that 0 is equals to Uy minus Gt. And by change of subject formula, we know that Gt is equals to your Uy. And then by the time you put your substitution now, because we know your Uy is U sine theta, we have that Gt is equals to U sine theta. And now that gives us a good time to actually get your T, actually the time to reach the maximum height. So by the time you divide both sides, remember we had that Gt is equals to U sine theta, and by the time you divide this by G and divide this by G, cut, your T is going to be U sine theta over G, where your T is time to reach the maximum height, time to reach maximum height. So the time to reach the maximum height, and that derivation led us to here. Now that we have this sum, so we already have that. So how about the time of flight now? So your T, your capital T, okay, let me leave some room for Vy, because your Vy says is the vertical component of final velocity. So now let's get the time of flight from there. We know that time of flight is basically 2 multiplied by the time to reach the maximum height, because it needs to return the entire journey down. So that's why they get your 2 multiplied by the T we already got from there by substitution. Let's call it equation 2. So we have 2 times U sine theta over G, and that your capital T is equals to 2U sine theta over G, your equation 3, where T is equals to time of flight. So that's how we have the time of flight. So that's the derivation for that particular time of flight. You can see it's really an interesting phenomenon when you always recognize that your Vy is equals to U sine theta minus Gt, where your Uy is your U sine theta. So I believe I should probably even just write it there. Your Vy is equals to U sine theta minus Gt, and that is it there. So we've gotten the time of flight now, and then the next thing you should probably check is to how to get the maximum height. I believe that should be an interesting phenomenon as well, and let's do that in the next part of the video. Now for the maximum height now, because we've gotten the time of flight, so that's very interesting. We got the time of flight already. T equals 2U sine theta over G. So for your maximum height is the next interesting part now. So your maximum height. So how do we deal with the maximum height now? So let's write our same parameters now. We know that at the maximum, we know of course our Uy, because we are still dealing with the maximum. So your Uy is basically U sine theta, and then we know that your acceleration is equals to minus G. More importantly, we know that at your maximum height, your Vy must be 0. That's an important thing you should know. Your vertical component of your final velocity is 0 at that particular point. That's what happens there. So how do we find the maximum height? That's the interesting thing now. So we've already used up our first equation now, your v equals to u plus at, in finding the time of flight. The next thing to do is to find your second equation, your v squared equals to u squared plus 2as. And now let's apply it there. So if you write the equation as it is from equation of motion, your v squared equals to u squared plus 2as. Now let's apply it in the translation for projectile. We expect it to be that vy squared equals to uy squared minus 2g and an h, right? So at any height it is h, and we have this like that. So but then at the maximum height, at maximum height, at the maximum height, let's call it capital H, right? So at the maximum height, we know something is definitely going to happen. Your Vy must be 0. So by substituting it, you know that your Vy is 0. 0 squared is equals to your Uy all squared is your U sine theta all squared minus 2g, and we have here what? Your H, capital H, like that. So if you go on, you will say your u0 equals to your u squared is u squared, and sine theta squared is sine squared theta minus 2gh. If you collect your like terms, or you try to make h your subject formula, you know that your 2gh is going to be u squared sine squared theta. By the time you divide by 2g and divide by 2g, this cut this, and your h must be equal to u squared sine squared theta over 2g. So now we've got the maximum height as well. And if you look at this, is exactly the result we've had in the initial video for projectiles, in the initial calculation. And that's how it works. The maximum height of a projectile is given by h is equal to u squared sine squared theta over 2g. It all depended on your equations of motion and the understanding that you had to break your vertical and your initial your horizontal motions away from each other. And that's how it works, and that's how your formulas came to be if you follow the mathematics. So your vertical motion is so good. It gave us two things. It gave us the time of flight, and then it gave us the maximum height. So now that is where your maximum your vertical motion could do. The next thing is for us to look into the horizontal motion to give us the third thing, which is your horizontal range. Now you may want to ask a question: why couldn't we use the vertical motion for a horizontal range? Now if you think through it, now if you see that your horizontal range, what is the definition for it again? Your horizontal range is the distance, the horizontal distance between the final place the projectile landed and where it was initially projected. Now in that definition, does anything sound vertical in the derivation? I don't think it does, and I hope you agree with me as well. The name is horizontal range. It is a horizontal distance, and so therefore we are making use of the horizontal motion. And that's what we do in the next section as well. So let's get into it. Alright, so now let's discuss the horizontal motion. So if you remember from the initial first part of this particular video, we said your horizontal motion is your uniform velocity motion. That's in a case where the velocity throughout is the same. And that is because, why? Because your horizontal motion is unaffected by gravity. So your vertical motion is affected by gravity, but your horizontal motion is unaffected. And because your ball or whatever your projectile is off the ground, we don't see the friction due to objects in contact. We don't have your friction there. There's friction in the air, which is called viscosity, but we are not really considering it in this in this particular scenario, we say it is very negligible. So for all purposes, our horizontal motion is a uniform velocity motion. And from previous work, we know that the only mathematical equation of motion for a uniform velocity motion is this one, which is your S is equals to ut. Your distance is equals to speed times time. Distance is equals to speed times time. So let's start from that same equation and see what we can achieve in our world of projectiles. So your horizontal motion. So in the case of your horizontal motion, of course, your velocity, your initial component of velocity is now going to be ux, which you got to be u cos theta. In case you are there's any doubt, your vx is also going to be your u cos theta. That's because it is a uniform velocity motion, so the velocities are going to be exactly the same. So your vx and your ux are the same, no gravity here. In the case of your vertical motion, your vy is your uy minus gt, which is what we said somewhere here, your equation 1 here. Your vy is uy minus gt. The gravity is being affected there. So here your vx is your ux, basically. So now how do we move on from here? We know that for your uniform velocity motion, we know that we are using something called a distance equals to speed. Now it doesn't matter because your initial speed or your initial velocity and your final velocity are the same, so it doesn't really matter, does it? So your distance is equals to speed times time. If you translate it into the world of projectile, your distance is your what? Your horizontal range for the horizontal motion, because that is the horizontal distance that has been traveled, right, from where it is sent to where it's ended. So your distance is now a range r, and your speed, we said it is your ux, so let's just call it your ux here. Whether we use ux or vx, it doesn't matter, but for the sake of consistency, let's just call it ux, because every of our distance we're carrying uy like that. And then time. So what time are we going to reference here now? Is it going to be the time to reach the maximum height or the time of flight? Let us listen to it now. The horizontal range defines it as the time it reached back to where it was projected from, and that happens when at the end of the motion. At the end of the motion, when everything has already what? Transferred to the end again. It's not when it's reached the maximum height, which is about halfway there, but then not quite at the end. So that means your time in this case is your time of flight. Please always note that then. So we have that to be your time of flight, which is your capital T. So that's how we've translated this into your world of projectiles. So how do we now put everything together? We say your r is equals to your ux is the same as your u cos theta, and your time of flight, let's remember the formula was 2u sine theta over g. So let's have the formula like this. Your u times u is what? Your u squared. Now it's multiplied by sine theta times 2. Your cos theta times 2 sine theta is your 2 sine theta cos theta over g. Now one thing from mathematics is that whenever you see your sine theta cos theta, your 2 sine theta cos theta is a substitution for your sine 2 theta. Your sine 2 theta says 2 sine theta cos theta is a trigonometric substitution. So if you don't understand or know how it is, please, this is one of those things you have to take as it is. You may find that in your trigonometry class, but that's not our scope of this video. So your sine 2 theta is equivalent to your 2 sine theta cos theta, and you still have your g there. So we can finally rewrite this as r is equals to u squared sine 2 theta over g. So that is it now. We've finally derived the formula for horizontal range as well. So your r is u squared sine 2 theta over g. Your h is u squared sine squared theta over 2g, and your time of flight t is your 2u sine theta over g. So that is how they got those formulas that we worked in with we worked with in the past. We've seen how it is derived, but then what is the main point now? What is the essence of going through this derivation? Are you expected to solve using this lower form, this your derivation every time you need to solve? The answer is no. They've done the derivation for you, but then the main point for you is that you need to understand the consistency of how important your equations of motion is, and understanding what your uniformly accelerated motion is and your uniform velocity motion is. The moment you understand those concepts and you bring them into the world of projectiles and understand from vectors that you can break this to the vertical component and the horizontal component, you have this. So having this kind of understanding, I can actually bring about new questions to ask. For example, I may just give you a question of a projectile and ask, what is the initial velocity of the what is the horizontal component of the initial velocity? And of course, your horizontal component of initial velocity is basically your ux, which is u cos theta. I may even ask you, what is your vertical component of your final velocity at a certain height? Now at that certain height, now it may not necessarily be your maximum height, because the only time your vertical component of final velocity is 0 is at your maximum height. So you can rely back on this your lower form of equation, your vy squared is equals to uy squared minus 2gh, where your uy squared is u sine theta. So my hope with you is that you really understood what has been taught, and I want you to also go through the entire derivation yourself so that it sticks to you and you really are able to see it. So in future classes, we'll twist some projectile questions where you'll be making use of these values, this your derivation, not necessarily your h, your r and t that we've seen before, but your in between steps, like that, like your initial velocity horizontal component, your final velocity horizontal component, and that's of the uy and the ux as well. But also, more importantly, we will pay more attention to your other scenarios. So in the case where your object was thrown vertically upward, that is your vertical projection, or your object is thrown horizontally, your horizontal projection. In the first case, there's a 90-degree between the object which is going up and the ground, and the other case there is no angle at all because it was thrown parallel to the ground. So for this video, of course, the scope is just when it is at any other angle aside from your vertical projection and your horizontal projection. So I hope that has been a good one. Thank you for listening. We'll catch up in the next one.